Good morning. Now we'll continue to study the so-called linear transformation, and I briefly recall the main idea of the last lecture. We start with our aim on this lecture to study the linear transformation. I will explain what does mean linear transformation, and we start with maybe some most simple example. Let the linear transformation is a mapping from one linear space, one vector space U, to other vector space V. And linear transformation is partial case of mapping. If we have mapping, we have let F be arbitrary mapping. I call that if we have mapping, we have some set which call domain of this mapping, and other set Y which called codomain. And we have rule which we can correspond every element of X, of capital X, some element Y which belong capital Y. And this rule is a rule which defines this mapping. Mapping is a triple: X domain, Y codomain, and mapping F. It's arbitrary mapping. Linear transformation is a partial case of such mapping. Example, the most simple example. Let U and V be arithmetical vector space R2. The element of this arithmetical space pairs of real numbers, the ordering pair. And let capital A be some matrix size 2 times 2, which element A, B, C, and D. And we can define the following mapping, which maps the element X of this vector space R2 into a product of this matrix on these vectors, the ordinary column-row product. I recall, by definition, the product of the matrix is defined by the following way. I multiply the row of the first multiplier on the column of the second multiplier, and multiplication first element on the first, second on the second, and after them I add these products. And by such way I obtain the first element of the product of this matrix, AX1 plus BX2. The second element of the resulting column is the product of the second column and the second row and the first column, using this rule CX2 DX2, and I obtain some vector column, the element of this vector space. This rule which defines this mapping. this mapping. This mapping has the following properties. Property linearity. If I consider two vectors, x, which is equal x1, x2, and y, which has element y1 and y2, and if I apply my matrix A to the sum x and y, by the definition, the sum of these vectors is sum of the corresponding coordinates, and the sum x and y will be the vector which has the following coordinates: x1 plus y1, x2 plus y2, and multiplication of the matrix A is element A, B, C, D on these vectors is equal, by definition, the first element of the column which is product of this matrix from this vector, and the second element is equal after them. I can use the definition of the sum of the matrix. The sum of the matrix which has the element which each of this element is the sum of corresponding element, and by definition this column I can present as the sum of the following column: A x1 by plus b times x2, the second element c x1 plus d x2 plus a y1 plus b y2 c y1 plus d y2, the main step. And the last sum is equal sum of the product a times x plus a times y. In this case, I have the following property of linearity, of so-called linearity of these mappings. What does mean linearity? If I have the arbitrary mapping, linearity means that we have the following equality. If let f be some mapping from U, vector space U, into other vector space V, and we shall say that f has the linearity, property of linearity, if we have following equality. If we have two vectors u and v, and f maps the sum into the sum of its images, namely f maps the sum u and v into sum of images f at u plus f at v for all u and v from from vector space U. The first property. And the second property in our example is the following. If lambda is some scalar and x be the some vector, by definition the product of the matrix A on the product vector x on scalar lambda is equal and I can rewrite the last equality as the sum as the product of scalar lambda on the and I obtain the next property, homogeneity. And we will say that mapping F has homogeneity property if we have following equality: F lambda x is equal lambda times lambda u is equal lambda times fu for all u which belongs capital U. We have two main property of such mapping, and this property, two property are equivalent the following one property: F lambda u plus v is equal lambda f u plus fv. And we obtain the definition of the linear transformation. Let as above u and v be the vector space over some field K, and the mapping F from u into v is called linear transformation. If this mapping satisfies the following two properties: F u plus v is equal fu plus fv for all uv which belongs capital U. Second property: F lambda u is equal lambda fu for all u from capital U. And you can note that these two properties are equivalent one property, one prime, F lambda u plus v is equal lambda fu plus fv. Easy to see that if we have only property 1 prime, we can obtain both this property. If we put lambda is equal 1, we obtain the first property from this. We can deduce this property. If we obtain v is equal 0, we obtain the second property. But if we have these two properties, easy to obtain this property. Easy to see. This some vector u1, and we can use the first property and obtain this term is equal the sum of these ones. And after them, we can use the second property and obtain the final expression. And this property is proved. And we have two equivalent way to describe the linear transformation. Maybe any question about definition? You understand? We can consider the some example, I repeat. This most simple example, linear transformation, and maybe more complex, this example 1. And let's consider example 2. Example 2. We can consider the maybe most complex example of the vector space. I recall that polynomial of the degree less or equal some fixed integer n forms the vector space. Is one of the example which was considered on the previous lectures in the last semester. And let U will be polynomials from variable t, which can have degree less or equal, for example, 2. The element of this vector space will be polynomial in the following form: a0 plus a1t plus a2t square. A sub I will be some real numbers. We will consider the set of such function. This function is polynomial. The sum of such function f t, the polynomial, and the sum of two polynomial. Let f the polynomial a1t plus a2t square, and this polynomial b0 plus b1t b2t square. The sum is defined as the sum of this polynomial as the functions, and we obtain the following sum: a0 plus b0 plus a1 plus b1t plus a2 plus b2t square. And we can also define the scalar multiplication by the formula L. Ft is lambda times Ft is equal lambda times a1 plus at plus a2t square is equal lambda a0 plus lambda a1 t plus lambda a2 t square. And we obtain this such vector space of the polynomials. And let's consider the following mappings, which is called by the letter capital D from this vector space, polynomial, vector space of polynomial into itself. And these mappings we define by the following formula, which mapping acts on the polynomial as a derivative. How act the derivative on the polynomial? We can write the exact formula. I recall that if we consider the polynomial of such type, the derivative acts on this polynomial by the formula a1 plus a2t square. And derivative has the following property of linearity. Derivative of the sum polynomial. If we have two polynomials f and g, the derivative of the sum is equal to the sum of the derivatives. And is equal df and dg. And second property, if we apply the derivative to the products, to the scalar product lambda and polynomial f, we obtain the derivative of the scalar product, and we obtain the product of scalar lambda on derivative f, and is equal lambda df. And we obtain that this mapping, which defined by derivative, is a linear transformation. Any question? You understand that example? So maybe enough important example of the linear transformation derivative. And we have the most simple example when we have deal with arithmetical vector space, and enough general example linear transformation which acts in enough arbitrary vector space. In our example, this vector space is vector space of polynomials. Question maybe? Yeah. Derivative. Okay. Let f be a function. And we can consider the following limit. Let's consider the graph of this function f. And let's fix some point x. And consider enough small number h such x0 plus h lies in the some neighborhood of this point x. And we can consider the images of this point f at point x 0 and the value of f in the point x0 plus h. And we can consider the difference of these values, which is equal h. And let's consider the ratio. If we consider limit of this expression as h bar tends to the 0, we obtain the so-called numbers, which is called the value of derivative in the point of x0. And we can consider some functions which correspond of arbitrary point x0, the value of the value which defined by such way. And this correspondence is a new function which called derivative. If we have polynomial t with degree n, the value of derivative, the derivative of this function is equal n times t in degree n minus 1. And the derivative of the polynomial is also polynomial. And we can consider the arbitrary polynomial, which is defined by the formula. And easy to see, the derivative has can be calculated by the following formula. Okay. I recall the definition from the course of analysis. Okay, have you any question? I need in the following properties of the derivative, properties of the linearity. We have two main property. If you have two functions, f and g, the derivative of the sum is equal to the sum of derivatives. And the second property, if lambda, let's some functions. If you have some scalar lambda, we can multiply the function on the scalar lambda, and we obtain the product of lambda on the derivative of the functions f. Okay? Do you understand what the derivative is? Main object in the mathematical analysis. And for us, in the context of our lecture, there is important the importance of this object is the following. The derivative is a linear transformation in the vector space of the function, and the main property for us of this mathematical structure. Maybe other question? Do you understand this example? Okay, let's continue. And we have two examples. The first example, the multiplication on the matrix, and the first example of linear transformation. And the second example, such structure is a derivative of the smooth function. Okay. Function which has derivative. In the second example, we have deal with the vector space of polynomial, and we can correspond to the polynomial the derivative or differential of such function, and this correspondence defines the linear transformation, which we will denote by D, and we shall call differential operator, the differential transformation. Differential transformation. And next step, we try to reduce the arbitrary case, the case of the arbitrary linear transformation, to the case of the linear transformation which is the matrix. We will try to correspond any linear transformation some matrix, which we'll call the matrix of the linear operator, the matrix of the linear transformation. The matrix of the linear transformation. Let capital U and capital V be the vector spaces. And let's choose the same basis. U in the space capital U base of U, and V is the base of capital V. If we choose two bases, we can correspond to any vector in this vector space X. We can correspond the coordinates of this vector. We can present this vector as a linear combination of the basic vectors by the unique way. And decompose this vector in the term of the basis vectors. And you can correspond the coordinates of these vectors. And we denote this coordinate vector column by the capital X with subindexes E, which denote the basis. And we obtain the so-called coordinate mapping. We denote this coordinate mapping by letter phi, index E. And we can apply to the arbitrary vector x the sum linear mapping. Let f be a linear transformation from u and v. Let f be a linear transformation. Now we correspond to this linear transformation some matrix, which we'll call the matrix of the linear transformation. The main idea of our correspondence is the following. Let u and v be the two arbitrary vector space, and f be a linear transformation. We have correspondence which correspond arbitrary vector x from the vector space, its coordinates. And coordinates of this vector we can understand as the element of the arithmetical vector space Rn. We can some mapping. Excuse me, phi. We use the letter which denotes the basis. This mapping is defined by the choosing of the base in the vector space. This mapping is uniquely defined by the base. U, phi u. U, the letter which denotes the basis. We choose basis in this vector space, and the choosing of this basis uniquely defines this correspondence. After them, we decompose the vector in terms of the basis vectors, and this coordinates is uniquely defined by the choosing of the base. And after them, we correspond to these arbitrary vectors, these coordinates, the coefficients of this linear combination. These coefficients is called coordinates of this vector, and we obtain one-to-one correspondence between elements of the arbitrary vector space and the element of the arithmetical vector space, excuse me, K is basic field, Kn. I'm sorry, Kn. K can be a real number field or complex number field. I try to use both situations, real and complex. And let we choose some basis in the other vector space V, and let V, V1, Vm be the base any other vector space capital V. and we have VU phi V other coordinate mapping. And we have two arithmetical vector space. And our aim to construct some linear transformation between this arithmetical vector space such the following linear transformation phi is to upper indexes u and v such that this linear transformation is a matrix. And this matrix will called the matrix of this linear transformation. This main idea of our construction. And now we try to realize this idea. How to construct such linear transformation. The idea is enough simple. We shall use the property of linear transformation. Let X be the arbitrary vector of the vector space capital U. And let's apply to this vector our linear transformation F. We can use this coordinate mapping and we can decompose our vector in terms of the vector of the basis E. And we obtain the following decomposition. The first step. After them, we can use this property, these two properties, property linearity. In this property 1 prime, I can write other scalar mu, and I can rewrite this equality in this form. After them, if I have more than 2 summons, in this case I have n summons, I can apply this formula step by step. Do you understand? I can present this sum as a sum, the first summons x1, u1, plus the other summons, we use summation from 2 to n, and apply this formula to the 2 summons. After them, I can repeat next step. On the next step, this transformation to the second sum, and by step, I obtain the following equality. Do you understand this? And I have images of the basic vector. And these images I can decompose. This element belongs to the vector space V. And I can decompose this element in terms of the basis of this vector space, in terms of the basis V. And let I have such decomposition. Let f u e is equal f e j v j. j goes the integer from 1 to m. M, the numbers of the basis vectors in the second basis. And that I have. These numbers is uniquely defined by the mapping linear mapping f, uniquely defined. Because uniquely define these vectors and uniquely define the decomposition of this vector in terms of the basis vectors. These numbers is uniquely defined. The coordinates of this vector and this basis. And these coordinates is uniquely defined by the sum itself images and by the basis. And after them, I obtain the following equality. After them, I can use the property of finite sums, and I can rewrite the last formula in the following form. I have the double sum. I can imagine this double sum in the form of such tableau in the entire of this on this matrix. I can imagine that lies the element of double sum. And the rows I summarize in the element of the row using the indexes I. And after them, I apply I apply the summing to the rows. I add the sum of the first rows to the sum of the second rows, and I obtain the sum of all elements of this matrix. But I can change the order of summands, and first of all, I can obtain the sum in the columns, and after them, I can to add the sum of first column to the second and other. And after them, I obtain the following sum. I change the order of summands. And I have the scalar product of this number, or the scalar product this, on the vector. And then I can use the axiom of scalar product, and I can rewrite this scalar product in the following form. Do you understand this transformation? I use the axiom of the vector space. I use this axiom. And using the distributivity axiom, I obtain the last expression express the last expression. I obtain the decomposition of this vector in element in terms of element of second basis V in the vector space capital V. I obtain the following decomposition. The coordinates of this vector, these coefficients from this basic vector, the first coefficients F1 J xj, and the last and I obtain the coordinates of the vector fx in the base u, the coordinates of this vector. And I obtain the following correspondence. If I start with coordinate vector x in the basis v, I obtain these coordinate vectors. What does mean this correspondence? What does mean this correspondence? I start with coordinate vector xv, and I obtain the following coordinate vectors. Coordinate vector What does mean this correspondence? Can you explain me what does mean this coordinates? You obtain the column row column row multiplication. You have let's rewrite this equality as multiplication. The following I can rewrite these coefficients as the row, the first row. And if I multiply this row on this column, I obtain exactly this equality. This equality row-column multiplication. Can you see this fact? Okay. And for the second row, by the same way, I obtain the multiplication, column row multiplication of the second row of this matrix on this column, and the last row has the following form. And this result I obtain the coordinates of the image of the vector x in the basis V. This element coordinates vector x in the basis U, I'm sorry. And I obtain the same matrix. And I will denote this matrix by F with two upper indexes U and V, which denotes the bases U and V. And I obtain the following formula. The main result of our reasoning, the following main formula. By definition, the matrix FUV of the linear transformation, the matrix of the linear transformation F from U into V in the basis U and V is defined by the following formula. For any vector x, the image fx, the coordinates of this vector in the basis V, by definition is equal product of this matrix UV on the coordinate vector XU. We obtain the formula, and this formula is the definition of the matrix of the linear transformation. This formula for us will be definition of the matrix of linear transformation. And our reasoning shows how this formula can be obtained by the natural way. And this matrix I can consider as the linear transformation from arithmetical vector space x up m to the other arithmetical vector space x up m. Any matrix, any multiplication by the matrix can be considered as the such linear transformation from one arithmetical space to other. The most important and most simple example of the linear transformation. But our reasoning shows that general case can be reduced to this partial case of the linear transformation by multiplication on the matrix. This matrix, we can consider this matrix as the coordinates of the linear transformation, roughly speaking. Any question? Do you understand this most important fact? The main idea, we reduce the arbitrary linear transformation to the partial case linear transformation, which is multiplication on the matrix. And this matrix is called the matrix of linear transformation. That's all. Maybe a question? One or more question? Do you understand? This first important point of our lecture, the definition of the matrix of linear transformation. I suggest consider some simple example of such situation, maybe more simple example. The matrix of the derivative. Let, as above, derivative be the linear operator or linear transformation from vector space R T is sub-index 2. I consider the polynomial which has degree less or equal to, and first of all, before to consider our example, I would like to introduce some notation. If vector space U and V are concise, the linear transformation is called linear operator. Linear operator. It's called linear operator if U is equal V. If domain and codomain are concise, linear transformation is called linear operator. It is called matrix of linear operator. I will denote f with one index. If two bases are concise, I will use only one letter U for this notation. And the example of the linear operator is most interesting example of the linear transformation. I explain later because this fact is right. And turn into our example. We have the linear operator, which is derivative in the polynomial vector space, and let's choose some simple basis in this vector space. What's maybe some simple basis in this vector space? Easy to see that the basis of the monomial, namely 1, that U1 is equal 1, U2 is equal T, U3 is equal T square. And what's the rule? How we construct this matrix? Easy to see that the columns of this matrix is the coefficients of the decomposition of the images of the basic vectors. How we obtain this column? I apply our linear transformation to the first basis vector in the domain, and these images I decompose in terms of the basis vector of the second vector space. in the terms of the basis of the codomain. How I obtain the second column of this matrix? By the same way. I apply my linear transformation to the second basis vectors, and this image decompose in terms of the basis of the second vector space of the domain. And I will do in our example the same way. I apply our linear operator to the first vector and decompose the image in terms of the basis vector of this vector space. In this example, domain coincide. I have only one basis. And first basis vector u1, and I apply our operator d to this vector u1. What does it mean? I apply derivative to this function 1. I calculate derivative of 1 is 0. The derivative of the constant is 0. And I explain the 0 polynomial. And the decomposition of this polynomial is trivial linear combination. 0 times 1 plus 0 times t plus 0 times t squared. And this coefficient forms the first column of my matrix of this linear operator. Okay? Agree with me? Maybe. I obtain the first column, 0, 0. I write them as a middle blackboard. The next step, I apply my operator to the second basis vector t. What does it mean? I calculate the derivative of the t. What I obtain by 1. Yes. Is equal 1. 1 is the polynomial, and I can decompose this polynomial on this basis. And I obtain 1 times 1 plus 0 times t plus 0 times t squared. And I obtain the second column of my matrix. And last column is a result of application of our operator d to the third basis vectors u3. u3 is t squared, and I calculate the derivative of monomial t squared. Using the formula, I obtain what? 2t, exactly. And I obtain the agree with me, yes. But I can choose other bases. For example, how to change the matrix of the operator if I change the basis. For example, I suggest to consider other bases. V, for example, V1, V2, V3, the ratio t squared 1, 2. How to change our matrix in this case? I change only third basis vector. I change t square on the ratio t square and 2, the ratio t square 2. How to change? Yeah. This. I must apply this derivative to the ratio t square on 2, and I explain in this case 1 times t. And I obtain this matrix dv. We have considered the general question. If I have two bases, u and v, what can we say about relation between the matrix into arbitrary bases? How to explain this relation? Maybe a question about these examples. Do you understand? The answer is the following. All right, the answer on the blackboard. We have two bases, u1 t square, v1 t squared, the ratio t squared 2. And we have linear operator is defined by the following rules. D is a derivative. D maps the polynomial to the derivative of this polynomial. And we obtain the matrix of these operators in the basis U, the matrix the following, and the basis V, matrix we want to study the relation between such type matrix in the general case when we have two arbitrary bases. What about time?
4 minutes left.
4 minutes. 4. Okay. Let's consider the more general case. We have arbitrary linear transformation. And let's consider two bases in U. Let U1 Un be the old basis and U tilde be the new basis in the vector space U. And the same way, you can consider two bases in the vector space V. V1, Vm, and V tilde, V1, Vm. And you can consider the matrix of transformation of the first basis to the new basis. Let C be such matrix. U times C is equal U prime. And by the same way, let D be the matrix such that V times D is equal U tilde. This N times N matrix and this M times M matrix. I call if we have coordinate vector x in the basis U. Let x is equal U xu equal U prime xu prime. And easy to see that coordinate of this vector in the old basis can be expressed as a product of the matrix C on coordinate of the vector U in the new basis. Really, if you substitute and express xu as using this formula, if you substitute U as U times C, you obtain U times C xu and U C. And if you compare this expression and this expression, and we know that decomposition of the basis vector is unique, we obtain from this equality, it follows the equality of the coordinate vectors, namely this equality. The same way we obtain, yes? Yeah. U is the matrix row, yeah, is exactly. And I multiply this matrix row on this matrix by the row column rule. And we consider this relation in the last semester, and briefly recall this notation. And let Y be the image of X under the linear transformation F. Let Y is image. Y is equal Fx. And for Y, I have the same relation. Y is equal V x V and is equal V tilde x V tilde. And V times D is equal, yeah. Time is over. Okay, 1 minute, 1 minute maybe. I can write the answer. The expression is the following: f u v tilde and f u v. U C the answer is following, but in detail we consider this relation in the next lecture. The main idea of the answer, the matrix of the operator in the various bases, is similar. We have the following relation. Excuse me, my time is over, and we continue in the next lecture.